Hello, my name is Mihm. I'm a third-year graduate student in the Shepherd Group at the University of Iowa. Today I will be discussing the convergence of coupled cluster to the thermodynamic limit using the transition structure factor in solids. The main take-homes will cover how our analysis of the coupled cluster correlation energy finite size effects show a convergence rate of n to the negative one-third, as well as how analysis of the transition structure factor shows this rate will eventually cross back over to n to the negative 1. One of the common questions in my field of research is, can I use coupled cluster theory for solids? Coupled cluster is a common method for things such as benchmarking due to its good balance of cost and accuracy, able to obtain results that are systematically improvable to the full configuration interaction limit, as well as produce exact results at certain limits. In solids, however, there are drawbacks that currently limit its use, including cost scaling with system size due to the finite size effects. This leads to reliance on extrapolations and convergence rate to obtain thermodynamic limit results. There's been a lot of work done to help address these issues, including using twist averaging to reduce finite size effects, as well as determining how different basis sets affect these extrapolations. Our work focuses on how the finite size effects of the coupled cluster doubles correlation energy in the metals modeled in the UEG converge to the thermodynamic limit. When we analyzed a log-log plot of the finite size effects in the high density, we found a convergence rate of n to negative one-third. As a typically accepted rate is n to negative 1, these results were unexpected. Recent research on coupled cluster in solids have shown a new, non-observable property dubbed the transition structure factor. This property is derived from the correlation energy expression and contains all information about the correlation in the system. Due to its relation to the correlation energy, the structure factor can be evaluated to determine the convergence rate of the correlation energy for solids. The literature results for analysis on the structure factor at small g show a convergence rate of n to negative 1. However, as previously stated, our results show an n to negative one-third convergence rate. So what's happening? To evaluate these power laws, we analytically determined the functional form of the structure factor and used it to evaluate the convergence to the thermodynamic limit. This graph shows the convergence of the remaining finite size effects in the system after the thermodynamic limit extrapolation. As can be seen, the n to negative one-third convergence works in an area of large G or sparse sampling, such as the high density, but tends to overcorrect as it approaches the thermodynamic limit. The n to negative 1 is a much slower convergence, but is much more reliable, especially in the small g range. Therefore, we determined that there was a crossover point between the n to negative one-third and n to negative 1 power laws around the peak of the structure factor. This crossover is then reflected in our data at large RS. Building off this analysis of the structure factor, I am currently mentoring an undergrad who is using machine learning to see if we can fill in some of the gaps in our structure factor data. We are currently working with a simple GPR model, which Laura will be talking about in another lightning talk. Preliminary results for the evaluation of the thermodynamic limit show promise for this approach. We are planning on continuing on to neural networks to help create a robust code that can evaluate the structure factor for a range of solids for use in applications such as the study of phase transitions.